you were in the south of England in 1944, you know this as the Flying Gasworks. In the rest of Britain, it was known as V2. But in Germany, the land of its birth, it was called the A4 rocket. And on the evening of the 8th of September 1944, the first A4 landed in London. More than 1,000 rockets were aimed at London, and most of them were launched from The Hague in Holland. Not far from the historic Palace of Peace, right in the center of The Hague, was an ordinary city street. This street was cleared of traffic and pedestrians for a couple of hours, and then a rocket was ready for launching. This is an actual launching site used by the Germans. You will see how little special preparation they required for firing a rocket. They wanted protection from the RAF and from the wind. The rocket was always placed on a launching table, in this case in the middle of the avenue of trees. These trees are just about the same height as a rocket on a launching table, so conditions were pretty good. This should prove to you that a rocket can be launched from almost anywhere. An area 23 feet square is sufficient, provided it can be approached by vehicles. The Germans fired from town or country. Along this avenue, there were 9 separate launching sites. A wood is the ideal site for rocket launching, as long as you can get in and out of it easily. Aiming marks were painted on trees, and a pit was dug for the firing control vehicle. The firing troop commander was in this vehicle about 30 yards away from the actual launching site. In a wood, the ground has to be leveled, and you must put down a firm base to support the launching table and the rocket. The Germans used wood or steel sleepers to provide this base. The Germans fired their last rocket against Britain in March 1945, and we took over after that. We collected damaged rockets from all over Germany and decided that the German scientists and technicians would fire some more rockets, but this time under British control. Much of the rocket equipment had been blown up by the retreating Germans. We had to reassemble it, find out how it worked, and make new equipment for ourselves. A thing like this had to be turned into a workable launching table. We reconstructed equipment, we made new vehicles, and we finished by making complete rockets from captured equipment. Sometimes luck was on our side, as when we found a factory in the British zone which was producing road transporters for the local farmers. These road transporters, known as Wiedelwagens to the Germans, are used for carrying the rocket. So the factory started to make them for us. Among the vehicles we reconstructed was this one, used by the Germans to convey liquid oxygen from the railhead to the launching site. At Cuxhaven, we took over a gun testing range and put up some new buildings, such as this proofing tower, where the rocket stood while undergoing some of its tests. Very soon, we had our own repair plants at work, where we assembled rockets from captured German equipment. Besides shelters for rocket parts, we built workshops, sheds, and stores. We captured a large number of German components: aluminum tanks for alcohol and liquid oxygen, and cylindrical drums containing rocket warheads. The tanks for holding alcohol and liquid oxygen are extremely light, although they're so large. The capacity of one of these tanks is approximately 4.5 tons of liquid oxygen. Yet 4 men can carry an empty oxygen tank without any difficulty. The mechanism of the rocket is best studied in diagram. The rocket is driven by the reaction of a jet of high-speed gases. This jet of gases is produced in the venturi or combustion chamber in the rocket by the combustion of alcohol and liquid oxygen. Here is an actual combustion chamber. It is made of steel. The pressure in the venturi is very high during burning, and to force the fuels in, the rocket has two pumps, one for each fuel. These pumps are driven by a turbine placed between them. This turbine develops 600 horsepower, since 8.5 tons of fuel have to be pumped into the combustion chamber in the space of 60 seconds. Here is the complete unit, turbine and two pumps. The turbine is driven by steam, which is produced by the chemical reaction between hydrogen peroxide and sodium permanganate, contained in these two tanks. Forward of the tail unit are the two fuel tanks. First, the liquid oxygen tank, then the alcohol tank. Here they are during the assembly of an actual rocket. Owing to the shape of the rocket, the alcohol delivery pipe has to pass through the center of the liquid oxygen tank. Finally, in the front of the rocket, we have the control compartment and the warhead. In the control compartment are two gyroscopes. These gyroscopes are the brains of the rocket. They are in universal mountings. Electrical pickups measure the movements of the gyroscope and translate these movements to the carbon vanes and the trimmers in the tail unit. These vanes and trimmers direct the rocket, both in bearing and elevation, along its trajectory and prevent any deviation from its planned course. The four vanes are in the jet of the rocket, and there is a trimmer on each of the four fins. This mock-up represents the inside of the control compartment in the rocket. In the background is a skeleton tail unit with the vanes and trimmers in position. As the control compartment moves, the gyroscopes move in their mountings, and these movements are conveyed through electric cables in the rocket to corresponding servo motors in the tail unit. There is a servo motor for each carbon vane and trimmer. The servo motors move the vanes and the trimmers to counteract the original movement of the control compartment and to keep the rocket on its course. This gyroscope controls the elevation of the rocket by moving a pair of the carbon vanes, thus turning the rocket from the vertical over to an angle of 43 degrees. The other gyroscope controls the direction of the rocket by the movement of this pair of vanes. These four vanes, made of carbon to resist the heat, are situated in the jet, and they can control the rocket only while the jet is burning. This period of control lasts for 60 to 70 seconds and covers the first 20 miles of the trajectory up to the all-burnt position. When it has reached the all-burnt position, the rocket is a free projectile, just like any artillery shell after it has left the muzzle of the gun. This is what actually happened when the Germans fired on London from The Hague. The distance is nearly 200 miles, the maximum range of the A4. The rocket was controlled for the first 20 miles of its flight, or until the jet had stopped burning. At this point, its velocity is 6,500 feet per second, and it is at 43 degrees angle of elevation. It keeps on climbing until it has reached a height of 50 miles, which is halfway on its journey. Then, still traveling towards London, it starts to fall. But it is slowed up to a velocity of 4,000 feet per second by the resistance of the air. It actually strikes the target at 4,000 feet per second, or nearly 3,000 miles an hour. The whole journey takes only 5 minutes. By comparison, a 16-inch gun will fire a 1-ton shell about 25 miles. The highest altitude that man has yet reached is about 12.5 miles, accomplished by 2 Americans in 1933. In the workshop which we built at Cuxhaven, German technicians and engineers under British supervision built rockets from the parts we had collected. Here are A4 rockets in various stages of construction. First of all, there are the 2 fuel tanks. one for liquid oxygen and one for alcohol. They're in a half shell padded with glass wool. This rocket has the motor attached to the tank compartment, which is now complete. The other half shell has been added. But the control compartment is not on the rocket yet. Now we see a tail unit ready to be added to the rocket. Wiring is being connected so that the rocket can be tested for electrical continuity. The control compartment has been fitted to this rocket. There's a complete rocket. It was painted black and white so that we could see it more easily when it was fired. Now the rocket, to be tested, is connected to a compressed air line. The tanks and pipes are tested for leaks by air pressure, and at the same time, all the electrical circuits are checked for continuity. When the tests are completed, the tail unit is added to the rocket. At the other end, the warhead is secured. This wasn't the normal German practice at this stage, but we wanted the warhead on the rocket so that we could lift it into the proofing tower. Then the rocket was lifted from the assembly line onto a transporter. It was then taken to the proofing tower so that the control apparatus could be adjusted. The rocket was placed in the vertical or launching position in the proofing tower. The gyroscopes and the control units were inserted, and the steering tests were done. To do this, the axes of the gyroscopes were lined up with the axis of the rocket. When the tests were completed, the rocket was ready for firing. We transferred it directly onto an elevator transporter known as the Meilerwagen to the Germans. When this stage was reached in wartime, the Germans used what they called the hot cakes method. They put the newly tested rockets onto a train and sent them straight to the railhead in the firing area. The Germans almost always fired a rocket within 3 days of its production, because they found that the number of failures was seriously increased by long storage. Now we are going to follow the operational procedure used by the Germans, starting at the railhead. At the railhead, the rockets were taken over by the technical troop of the rocket regiment. The German railway wagons were not long enough to carry a rocket, so the system was to load 2 rockets onto 3 railway wagons. The rockets were loaded without the warheads, which were carried separately in the middle wagon. The first job the technical troop had to tackle was the lifting of the rocket from the railway wagon to the road transporter. A mobile crane is used to lift the A4.